Good evening. Today I'll be discussing the solutions for week 1 and week 2 quiz. Week 2 quiz. I hope you have submitted the assignment and I'll start. So, the first question here in week 1 assignment. Yes. So, the solution. The first question for the week 1 assignment is, what is the unit of surface tension? So, surface tension here, gamma. Gamma, we know that for any interface, for example, the surface tension acts along the line. That is, so therefore, we can say, and therefore, we can say the surface tension force gamma has the units of Newton per meter. But you also see that there are other definitions of surface tension that we need to be careful of, such that gamma is also referred to as the amount of energy, or more precisely surface energy used in creating the surface of the interface. This is the first definition. The second definition, where it is gamma, can be said that joules per meter square. But if we look at the options, we have only joule per meter, and therefore this is incorrect. The only correct option here is A, which is Newton per meter. Newton per meter. This is a fairly simple question. And moving on, we have the second question where we say, consider a spherical drop of radius r. Radius r of a fluid A in fluid B, if gamma AB is the surface tension of A and B, what is the expression for the capillary pressure jump across the interface? So if we make a schematic here, the surface AB, there's a drop of fluid A in fluid B. So this is fluid A, this is fluid B, and along the interface acts gamma AB. So we are asked what is the pressure jump, capillary pressure jump across the interface. That is, we are asked find delta P, that is P in A minus P in B. If we recall the Young Laplace equation, or the Laplace equation says that the pressure jump is related to surface tension as gamma times the curvature, or in other words, gamma times r mean. Here we say that it's a spherical drop and the surface tension is gamma AB. Therefore, we can write after substitution that P pressure in A minus pressure in B is equals to gamma AB times the mean curvature, that is, sorry, uh, that is 1 by R plus 1 by R, which is equals to 2 times gamma AB by R. Notice the sphere, a sphere, as we have seen in the class, has two equal curvatures along perpendicular axis, that is 1 by R, and in the perpendicular direction it is also 1 by R. Therefore, the correct answer here is C, that is delta P is equals to 2 times gamma AB by R. So here in the third question we have, if there are five forces involved in a phenomena, how many unique non-dimensional numbers that can be constructed? So here we have five forces. That is, let's assume different forces. We have inertia, viscous forces, gravity forces, surface tension force. So these are the five forces we have. And if we want to create non-dimensional groups, Then we have the non-dimensional parameter pi as a force balance. That's the simplest way of creating a non-dimensional number. So we have force A by force B. So let's first say we can make pi 1 is equals to, we'll keep inertia as constant and then vary the other forces. Inertia by viscous, inertia by gravity. We have pi 3 as inertia by surface tension here, and pi 4 we have inertia by electrostatics. These four non-dimensional groups are unique and can be made to find other non-dimensional groups which are a balance of, let's say pi 5, which is equals to, let's say we want viscous force by surface tension force, which can be written as inertia by surface tension and inertia by viscous, which in turn are simply just um, inertia by surface tension is this, which is pi 3 divided by inertia by viscous, which is this pi 1. Therefore, pi 5 is not a unique non-dimensional group and it can be generated simply by dividing pi 3 by pi 1. Therefore, the non-dimensional groups which are unique to a problem can be made by these four groups, that are pi 1, pi 2, pi 3, and pi 4. So the correct answer here is 4, which is 4 unique non-dimensional groups can be made. So moving on. Next we have the Weber number represents the ratio of which set of forces. Move this slightly above. So Weber number. So Weber number for us in interfacial in in, in interfacial flows can be defined as, Weber number here is WE. Sorry. Uh, Weber number can be defined as inertial forces to surface tension force. So let's go ahead and also derive the expression for the Weber number. And the procedure to derive the Weber number is also important. So let's have a look at it. Before that, I'll get some space here. So let's write down the momentum equation from which we can balance the different forces to get the expression for Weber number. Uh, Rho times U del U is equals to minus dp by, yeah, I'll write it in vector notation, which is minus grad p plus mu del square u. So this is the expression for us. Uh, so let's see. First, we have the inertia force. Inertia force can be written as um, rho. We can do an order of magnitude estimate, which is rho times u times del by del x u, which can be written as in terms of, if we non-dimensionalize u as u star by u and x as x star by L by LC, let's say, then we can write it as order of magnitude rho u times u by LC. That is the expression for the inertia force. Similarly, if we want to write, we know that in this particular problem, we have surface tension force is important. Tension force is important. Therefore, pressure P, therefore pressure P, P can be written as gamma times LC. This comes from the equation that del P is equals to gamma times R mean. We have non-dimensionalized R mean as R star mean by LC, and therefore we have order of magnitude gamma times LC. And if we see the pressure jump minus del P term scales as order of magnitude gamma by LC by LC. Therefore, if we balance the two forces, that is the inertia term and the surface tension term coming due to the pressure, we balance these two, then by the definition of Weber number, we have Weber is equals to order of magnitude of rho u square by LC divided by order of magnitude of, sorry, gamma by LC square, which is equals to rho u square LC square divided by gamma LC. Removing and putting, we have this implies equals to rho u square LC by gamma. This is how we get the non-dimensional numbers by doing a simple force balance. Uh, so the correct answer here is inertia to surface tension. Moving on to the next question. Next question we have. Let the scalar field F. So F is being defined as a scalar field. X comma Y comma Z is equals to x square plus y square plus z square. Then find del square F, where we know that del square is the Laplacian operator. So F here is a scalar field and Laplacian operator has been operated on the function F. So first we'll see how to get the Laplacian operator. So here if we write del, which is a vector, then del is given by del in Cartesian coordinates, where we are using the coordinate system as, sorry, x y and z. Then del by del x, oh sorry, del by del x I cap plus del by del y j cap plus del by del z k cap. Then the Laplacian operator del square can be written as del dot del, which is equals to del by del x I cap plus del by del y j cap plus del by del z k cap sorted with del by del x I cap plus del by del y j cap plus del by del z k cap. We know that I dot I cap is equals to j dot j cap plus is equals to k dot k cap, which is equals to identically 1, and I dot j cap is equals to j dot j cap dot k cap is equals to I cap dot k cap is equals to ij j k I k I j j k I k is identically equal to 0. I'll get some space here. Then we have del square operator is equals to del by del x, del square by del x square I dot I plus del square del y square j dot j plus del square by del z square is equals to k cap dot k cap, and the rest of the terms will be 0. Then we can write the Laplacian operator as del square by del x square plus del square by del y square plus del square by del z square. Now doing the Laplacian of of the scalar field f, we have del square f is equals to del square by del x square f plus del square by del y square f plus del square by del z square f, which is equals to del square by del x square of x square plus y square plus z square plus del square by del y square is equals to x square plus y square plus z square del square by del y square of f, then del square by del z square of square plus y square plus z square. Here we will get only the terms from x from, so this is y square and z square. Therefore we will get, therefore the answer to the question is 6, which is del square f is equals to 6. Here in the sixth question we have, in the continuum approximation, which of the below statements is true? The interface needs to be treated as a region of finite thickness. The interface is treated as the interface is treated as a mathematical surface with zero thickness. Curvature of the interface becomes negligible and density does not vary in space. So we'll investigate all of the options given. Uh, so the first statement says that the interface is of finite thickness. The second one, we say that the interface is of zero thickness. The third statement says that there is no curvature del dot and gap is 0. And the fourth is that density does not vary with space. So for the we know from the lectures that the interface thickness is assumed to be of order of angstroms. Therefore, even though the interface has a finite thickness, but for continuum mechanics, the thickness T interface is assumed to be of zero thickness. Only then can we implement the following jump conditions. Therefore, the interface is considered to be of zero thickness, and the option del dot n is equal to 0 is not always true. This is only a special case where the interface is flat. And the fourth option is that when the density does not vary in space. But if we have a container and a fluid, we see that this inside the fluid, in the bottom fluid, we have density B, and in the top fluid, we have density A. Therefore, we say that the density is not constant in space for points B here and A. Rho A is not equal to rho B. Therefore, the only correct option here is B. That is, the interface is treated as a mathematical surface with zero thickness. So again, we have a theory question where the question says, which of the below statements is true for a fluid-fluid interface with surface tension? So there is surface tension. So the options, we see that there is a comparison of pressure. Therefore, we resort to the Laplace equation, which says Laplace equation, which says that the pressure is equals to gamma times del dot n, or curvature. So we check the four options. The pressure is always continuous. So by continuous, we mean that when we move from the fluid B to fluid A, the pressure at point P, at a point very close to the interface, and the point very close to the interface from the top is PA, then PA minus PB is said to be continuous when the difference is zero. This implies that pressure at A is equals to pressure at B. So this is not the case. It is not always continuous. So sorry. So the first is incorrect. Pressure is always discontinuous. That means pressure at A is not equal to pressure at B. Again, this is not always true. So now we have, this is the statement A, option A, check. Yeah, not this. This is the equation. This is we're checking A, we have checked B. Now if the interface has curvature, that del dot n is equal to 0, is not equal to 0, that is it has curvature, then we have the RHS delta P is equals to gamma dot del dot n cap. Then there is always PA is not equal to PB, and therefore it is always discontinuous. And we will also check the B statement, which says that pressure is continuous across the interface only if the interface has curvature. So if del dot n cap is not equal to 0, that is it has curvature, then PA is equals to PB. This statement is incorrect, as we have seen above that the RHS of the equation is not 0. Therefore, the only correct option is C. Okay. So the next question, in this question, we have if the stress tensor is given as tau, that is, and the unit normal and n cap is the unit normal, then what is the expression for n dot tau dot n for the phase ABCD? We want the shear stress on the face, the normal to this interface, to this face is, and if we write down the normal vector for the face, normal vector for the face ABCD is given by n cap at ABCD is equals to 1 I cap plus 0 J cap plus 0 K cap, or in other words we can write 100. Then we have that the tau tensor, the stress tensor is given as tau 11, tau 12, tau 13, tau 21, tau 22, tau 23, tau 31, tau 32, tau 33. Then we want n cap dot tau dot n cap, which is equals to 100, tau 11, tau 2, tau 1, tau 2, tau 23, tau 31, tau 32, tau 33. Now we have we do the if we do the multiplication, we have 0 to tau 1 1 tau 1 2 1 tau 2 2, which is n plus which is equals to tau 1 1. Therefore, we have therefore we after performing the dot products, we have the solution to be tau 1 1. Therefore, the answer to the solution is n dot tau dot n is equals to tau 1 1. Now we have a question that if we have a velocity field u, which is given by the function given by the following expression, then if it is solenoidal, then what is the value of lambda? So we have u vector is 4x plus 3y I cap plus 3x plus lambda y j cap. And we say that u vector is solenoidal. Then we know that divergence of u vector is equals to 0. This implies that del dot u, which is equals to del, here del is a vector, del by del x I cap plus del y j cap dotted with u vector, which is 4x plus 3y I cap plus 3x plus lambda y j cap. So we have del dot u. This implies del dot u is equals to del by del x of 4x plus 3y I cap dot I cap plus del by del y of 3x plus 4y. Oh, it's not 4y, it's lambda y. Lambda y j cap dot j cap. Implies 4 plus lambda. And we know that for the vector u to be solenoidal, this has to be 0. This implies lambda is equals to minus 4. Therefore, for the vector u to be solenoidal, the value of lambda should be minus 4. u to be solenoidal after the minus 4. Now we have another question for the stress tensor, where we are asked if the stress tensor tau is given as shown here, that is this, and n hat and t hat are the unit normal vectors and tangent vector respectively, then it is also given that the tangent vector to the face ABCD is parallel to the y-axis. That is for the face. This is the normal vector, and the tangent vector is in the x direction. Then we are asked what is the expression for n dot tau dot t. So let's get some space. So we are given the n n hat vector and t hat vector, and we are asked find n cap dot tau dot t hat. So firstly, we will see what are the expressions for n hat. n n hat is along the y-axis, and it's a unit normal, therefore n hat is given as 0 I cap plus 1 j cap plus 0 k cap, which is equals to 0 1 0, and we know e cap is along the x-axis, therefore I'll just copy the figure here. Also have a small x. uh, so we have t hat as 1 I cap plus 0 j cap plus 0 k cap. Then for n cap dot tau dot p hat, we have 0 1 0 tau 1 1 tau 1 2 tau 1 3 tau 2 1 tau 2 2 tau 2 3 tau 3 1 tau 3 2 tau 3 3. So if we do the dot product here, it is 1 cross 3 3 cross 3 3 cross 1, which equals to 0 1 0 of the first column, which is tau 1 1 tau 2 1 tau 2 is 1. Then we have ngov dot tau dot t hat is equals to tau 2 1. Therefore, n dot tau dot t is equals to tau 2 1. So with this, we come to the end of the first assignment. I'll take a 5-minute break here. Back and we'll discuss the second assignment. Okay. Okay, now we'll look at the second assignment. The second assignment. So the first question is, let's get some space first. So the first question is, what is the surface tension of a spherical drop of radius 1 micrometer if the pressure jump across the fluid-fluid interface is 40,000 Pascal? First, we'll write down what is given. Radius 1 micrometer. One second. The radius is 1 micrometer or 1 into 10 to the power minus 6 meters. So we are asked to find what the surface tension is. So find surface tension gamma. So from Laplace equation, we have delta P is equals to gamma times the mean radius, which is equals to, it's a spherical drop, therefore it is 2 times gamma by r. This implies gamma is equals to delta P times r by 2, which is equals to 4,000, 40,000 into 1 into 10 to the power minus 6 divided by 2, divided by 2. So this gives us 0.0 Newton per meter or 20 millinewton meter. Therefore, the answer is B, 20 Newton, 20 millinewton per meter. So in the second question we have, which of the below expression corresponds to the Marangoni stress? So we have seen that we see Marangoni flows in surface tension dominant dominant flow phenomena where there is surface tension gradients. This means that we are talking about the tangential stress balance, which has the surface tension gradient terms. So tangential stress balance n dot tau dot t in the plus side minus n dot tau t in the minus side is equals to negative of tension dam del S dot gamma. Therefore, this particular term, which accounts for the sorry, unbalance. Therefore, the term minus t hat dot gradient of surface tension is the unbalanced term for the tangential stress. So this tangential stress therefore results in the movement or the Marangoni flows. Therefore, the term denoted in red is also referred to as Marangoni stress. Okay. The next question says, which of the below statement is true? If tangential stress is continuous across the interface only if gradient of surface tension is zero. Tangential stress is always continuous across the interface. Tangential stress is always discontinuous across the interface. And the fourth option is tangential stress is continuous across the interface only if gradient of surface tension is not equal to zero. So as we have already seen straight away, both the option B and option C are not true, and the tangential stress tangential stress across interface is equal to the dot product of surface gradient of surface tension and negative of this. So if we look at the option A and option B, the tangential stress is continuous only if shear stress is contain sorry continuous if RHS is equals to zero. This implies that surface gradients of gamma should be equal to zero. Therefore, option A is correct. Okay. We have we look at the next question. Get some space here. Now, if we look at it, consider a flat interface where the surface tension is increasing linearly from left to right. Which among the four velocity profile represents the flow in the below fluid? In the fluid below the interface. So if we have an interface, it says that the surface tension is increasing towards the right. That is it is low on the that it is low on the left side and it is high. Or simply we can say that surface tension is low here and surface tension is high here. So actually this figure, if there are more number of surfactants, the surface tension is low. Therefore, to being consistent, so here surfactants on the left are more, therefore the surface tension is low. And here on the right, the surfactants are less in concentration and therefore the surface tension is high. So we see that the surface tension force is given by the tangential stress, which is tau dot n dot tau dot p is equals to negative of dot gradient of s gradient of gamma. So gradient, the negative gradient of gamma is in this direction, and the shear stress can be written as d by dy. Therefore, the flow goes from left to right, left to right. Have a quick. So therefore, owing to the fact that the gradient, the surface gradient of surface tension is from right to left, the negative of the surface gradient of surface tension is from left to right. Therefore, we can analogously also look at it. I'll just get some space. This can also be analogously looked at like the momentum equation we have minus grad. Yeah, I'll change the color. We have minus grad P by grad X, where we say that the flow of fluid is always from the low pressures to the high pressure zone. Then, then the flow of fluid is from low pressure to high pressure. Similarly, for a negative, Therefore, the flow in case of a surface tension driven flow is from is from lower surface tension to the higher surface tension. So the analogy helps us visualize the flow. The other part is um, which of the profiles are correct. If we see only these three, the direction is correct. And if we look at profile C, then we see that the effect of surface tension on the interface is going constantly into the bulk, and there is no reduction of velocity, and therefore this is unphysical. As you can imagine that the viscous forces will start becoming important here. So therefore option C is incorrect. Furthermore, if we look at option D, there is there is reduction of pressure. There is reduction of velocity as we go down, but the velocity comes to a sudden standstill as if there is a wall here, which is not the case. The profile will looks like so only when there is abrupt slowing of velocity due to the presence of a wall, but there is no wall and the fluid goes into the bulk. Therefore, we need to have a profile. We need to have a profile to have a profile which starts from zero and slowly starts feeling the effects of the interface. Therefore, the correct option is option B. I'll re-emphasize what has been said. The option C is incorrect because the velocity profile is indifferent to the slowing owing to the viscous forces in the bulk, and option D is incorrect due to the fact that the velocity profile comes to the velocity goes to zero as we move down into the bulk at a certain distance d from the interface, and this abrupt slowing needs to have a significant d, and also it looks like it is due to the presence of a wall, which is untrue. Then the only option that satisfies the conditions where the velocity of the fluid is going to zero as we go into the bulk and increases slowly as we move towards the interface, which is only option B, sorry, option B. Okay. Moving to the next question. Which of the below statements is true if the surface tension gradients are present on the interface? Uh, so what is given here? Let's write down. Given is that surface F The surface tension is a function of x, y, and z. That is, the surface tension is varying along the surface of the interface. Then, then we can say that the surface gradient of gamma x comma y comma z is not equal to 0, and therefore the fluid cannot be held static as there will be tangential shear stresses, and which also means that the n dot tau, therefore option B is also correct. The tangential stress is non-zero. And finally, the interfacial velocity is directed from lower surface tension to higher surface tension. We have already seen this in the previous question, and therefore this is also true. Therefore, the answer to this question is all of the above. Okay. Moving on to the next question. In a hypothetical situation, if surface tension at the interface of a bubble is taken to be zero, then which of the statement is true? So again, we'll see which what is given in the question. So we can say that given is gamma is equal to 0. Gamma is equal to be 0. Then we need to comment about the pressure inside and pressure outside. Therefore, we'll use the Laplace equation. Using the Laplace equation, we have delta P is equals to gamma times RV. We are saying that it is a bubble. So so the surface tension gamma is equal to 0. Therefore, we have 0, which simply states that P in minus P out is equals to 0. This implies to P out. So therefore, we have the pressure inside is more than the pressure outside. This is not true. Then the pressure inside the bubble is same as the pressure outside. This is correct. Then the pressure outside is more than the pressure inside. Again untrue. The pressure inside the bubble is 0. This is also untrue. So the correct option is option B. So in question number 7, what is the mechanistic reason behind the tangential nature of surface tension? As we have seen in the lecture and also asked in the previous doubt session, the anisotropy of the long range attractive intermolecular forces near the interface, the unbalanced normal force on the surface molecules, anisotropy in the short range repulsive intermolecular forces, or the presence of charge in the surface molecules. So this is untrue. The anisotropy in the short range repulsive forces is also untrue. There is no charge on the molecules. The only correct option is option D, which is an anisotropy of the long range attractive intermolecular forces near the interface contributes to the tangential nature of surface tension. Now we have two questions which are coupled. Let's look at this question. Okay, we'll we'll cover both of the questions together. So consider a blob of fluid initially in a cuboidal shape of size 10 into 6 into 9 meter cube. If the surface tension, so again, sorry, if the surface tension is equal to 72 micronewton per meter, then what is the change in the surface energy as the blob changes to its equilibrium shape? Assume there is no gravity. So the crux of the question is change in surface energy as the blob takes its equilibrium shape. And the next question states that in the above equation, what is the radius of the sphere in its final equilibrium shape? So the second question basically gives out the hint that the equilibrium shape for a blob of fluid, if there is if the gravity is absent, is a spherical shape. So let's draw the figure. We'll take the blob of fluid. Initially, initially the fluid is of the shape of a cuboid. So it's 10 cross 6 cross 9. Then it moves to a, so the equilibrium shape will be, the equilibrium shape will be a sphere. Basically, the blob of fluid in the shape of a cuboid turns into a spherical shape in the absence of gravity. The important point is the gravity is equal to 0 in this particular case, or gravity is not important. So firstly, we'll calculate the radius of the sphere. So we'll have, let's say this is A, shape A, and shape B. So volume of A is equal to volume of B. Then we have 10 into 9 into 6 is equals to 4 by 3 pi r cube. This implies r is equals to, quickly calculate it, to 9 6 is equals to this divided by 4 by 3 divided by I. So we'll get the radius to be 5.05 mm. So the answer to the question 9 is A, which is 5.05 into 10 to the power minus 3 meter. And then once we have the radius, okay, I'll get some space. Okay, once we have the radius, we have to calculate the change in surface energy. Okay, so we have R as 5.05 meter. Then the sir, okay, change the color of the panel. Surface area of A is equals to twice into length into breadth plus breadth into height plus length into height, which is equals to 2 into 10 into 6 plus 6 into 9 plus 10 into 9, which is equals to t plus 9 plus 45. Which is equals to 204 millimeter square. Surface area of B is equals to 2 by 3 pi. Surface area is pi r square is 2 pi r square, which is equals to 2 into pi into 5.05 whole square, which is equals to 160.23 millimeter square. Then the surface energy will be, the total surface energy Surface energy is given by gamma times the change in surface area, because gamma is joule per meter square, and then we have meter square here, which gives joule, which is the unit of energy. Therefore, we have 0.072 into, okay, we will take uh 0.072 into 204. Okay, we'll have the final one, final first. 123 minus 204 to square. So mm's need to be changed to meters. Therefore, we have 10 power minus 6, which is equal to 6.0 into 10 power minus 6 joule. 6.3. It will come out to be 6.3. So now we have to decide what is the change in surface energy. So as we have change in surface energy, it will be negative as we go from 0 0.072 final shape minus initial shape. Therefore, the final shape has a lower energy, lower surface energy than the initial shape. And this is also true because that is the driving force, as the cuboid takes up more surface area and it's feasible in nature to be in the least uh, energy form. Therefore, it moves to a sphere. So, therefore, the answer to the question number 8 is B. 6.36. Finally, conventionally, surface tension is explained as a result of net unbalanced force between molecules fixed in space as one approaches the interface. This is a simplistic explanation, insufficient to explain the molecular origin of surface tension. So, generally, in class, we have seen that we say that molecules close to the interface have an unbalanced force. This explanation is incorrect because we always know that these molecules are not fixed and they constantly move around. Therefore, this is correct. This also fails to explain why the nature of the surface tension is tangential, as we can see that the unbalanced force is directed towards the bulk of the motion and not in the tangential direction. And also the third point, which means that the net unbalanced force is inside the bulk of the fluid. Therefore, all of the options is true. So, therefore, we come to the end of this clearing session. If you have any further doubt, I'll give my email. 20M22P100001 IITH dot AC dot in. If you have any further doubts regarding these, you can email me. My name is Bish. Thank you.